新加坡南洋理工大学的3年级的学生，我们都是就读宇航工程系。我们接下来即将用英文来讲。
我们可以用中文问
好，我们尽量用华文来。
没有，你们讲英文没关系。
好，可以。
我问问题用中文，我啦。
So once again, good morning everyone. This is our outline. Firstly, we'll do introduction, followed by system, mission procedures, calculation, modification, fail-safe, and conclusion. So, just a short introduction. I'll introduce the team. Firstly, this is our team leader, Lo Xianming, followed by Morgan, Ding, Adrian, and myself, Shi Qi. Our supervising professor will be Professor Yong Ki-Hu. Okay, so
here?
No, he's not with us.
但昨天有在场。
对，昨天在场。Okay, so this is the system. Basically, we can classify into 3 different components: the aircraft, the ground station setup, as well as the image capturing. So for the aircraft, basically components within the aircraft, such as the GPS module as well as the wireless telemetry, they are mainly for tracking and navigation purposes. Secondly is the ground station setup. Mainly these components are devices that we use at our ground station. So it includes our computer interface, wireless telemetry, as well as the high gain patch antenna, which serve to extend the range for our wireless data link. And for image capturing is for the purpose of capturing image and to locate the GPS coordinates of the target. So we have the HD camera as well as the GPS module. So this picture shows the aircraft. So it shows where our devices are located within the aircraft. So for example, for our RC logger Pro, which is our video camera, is located beneath the right wing. So these are just some technical details. So I'll move on to the mission procedures. So how we actually carry out our mission is pre-flight. We'll have the uploading of our flight plan, and we also have this checklist at the ground station. Basically, to keep track of what we have to do so that we won't miss out anything. And then our aircraft will be launched manually by the flying team. So during flight, the aircraft will take off from the ground station. We will launch it manually. When it attains stabilization, we will then switch it to autopilot mode. So as it approaches search zone A, it will be under autopilot mode. As it enters into the search zone, we will have performed a loiter and search sequence of decreasing radius. So it's something similar to this. So during the loiter and search sequence, the camera will be triggered and will capture image at 1 second intervals during the search sequence, during the search zone only. It will then proceed to the next search zone. As we enter into search zone B, we will perform the same search and loiter sequence, then return to the ground station. So after we perform our flight, post-flight will include extraction and analysis of the data. Analysis and extraction of data. And then we will actually search for the exact target. And then we will actually conduct photo enhancement and target recognition. So for our RC logger, our video camera, it actually is tagged with a GPS coordinate. So within the same frame, we can actually locate if the target is within the frame, we can actually locate the GPS coordinate, and that's how we actually extract the GPS coordinate. So these are the targets that we have identified during the competition. This is our target photos in search zone A, and this is for search zone B. Next, for fabrication and design, I'll pass it to Morgan. He'll do the explanation.
Okay, thank you, Shi Qi. My name is Morgan. Good morning, ladies and gentlemen, professors. I'll be dealing with the fabrication and design sections of this presentation. I'll be giving you a very brief introduction of the kind of equipment we have on our UAV. And first and foremost, I'd like to start with our autopilot module and the software. It's nothing new to most of you because I believe you guys are mostly using the autopilot Mega as well, based on the Arduino platform. Just a very quick introduction. It's basically a cascaded PID controller which uses GPS as navigation, to navigate. Very simple reason why we chose APM is because it is completely, it's a full open source, and it's very easily programmable in terms of the open source through the Arduino platform. And this is the mission planner that we use to make upload our flight plans and to extract data. Next, I'll go on to our wireless setup. For our case, we are using the XB telemetry wireless transceiver, and we have chosen the 900 megahertz ISM band to transmit our signal. One reason because the lower the frequency, we have a larger range. And through flight tests, we have successfully attained maximum radio frequency line of sight of about 10 kilometers. Nothing much about here. This is basically just our patch antenna, the one that we use to transmit our signal. Next will be our wireless transmitter. I understand that some of you guys may be using 72 megahertz, but for our case, we are using the 2.4, largely because most of us are newer RC enthusiasts. And the transmitter brand that we're using is actually the Fugava 6PX. And through this transmitter, we can very easily switch between auto and manual modes. And this is something new. What I think our group is especially more proud of and to present will be our camera mount and our camera. So this camera mount is basically we have a servo that is attached to it, and this servo is powered directly through PWM from our Arduino APM module. And this camera mount is in fact placed, as mentioned by Siqi, at the bottom of our right wing, because we want to take pictures of the ground perpendicularly, not at 45 degrees, so to speak, because we want an exact GPS location. What's good about this is that we have modified the source code in APM such that when the plane banks, with the servo, it will auto stabilize. So at any point of time, no matter I may be doing a loiter, I may be doing a bank, the camera will be always pointing and taking pictures perpendicularly on the ground. And next, the camera. We are very proud to find this commercial product in the market because, it mostly does most of the job for us. It's a camera, like as mentioned by Siqi, that is able to do GPS tagging to the pictures and the videos that we have taken. And this camera is a video camera. It has capability to take videos in 720p or pictures up to 5 megapixels. So for our case, we have done testing, to choose whether to take videos or to take photos, and we realized that pictures are really good. So in the end, we chose pictures over videos. And we have as well modified the source code such that we are able to trigger the video on button only when we enter loiter. And when we leave loiter, we will turn it off. All this technical stuff will be elaborated further by Adrian and Xieming later. And this is the program that came together with the RC logger, which allows us to work on the pictures as well as to extract the GPS data. In this plane, this picture you have seen from Siqi's slide, I'm just going to give you some reasons why we have placed our equipment at certain locations. Camera on the right wing at the bottom for reasons because APN only does loitering in an anti-clockwise fashion. If we go clockwise, then of course it's the left wing. If you guys observe clearly, on the left wing we have some weights. I think some of the judges, they were very sharp. They pointed out, hey, why do we need this over there? For reasons because we need to balance the weight. We have the camera on the right, we need a balance weight on the left. And why we place it on top of the wing is because, we don't want it to drop mid-flight. GPS modules, very small ones. Actually, we have two. One for the APM, which I think the first group have already shown. We have a special one for our RC logger and our camera to track the GPS coordinates of our pictures. And if you can spot, we have this tiny little thing over here. That's our electric speed controller for obvious reasons because it tends to heat up for extended flights. For info, for us, we don't exactly fly for the stipulated distance of about 6 km. We have in fact flew for about 12 km And when the plane comes back, the ESC in fact gets really hot. So we place it outside, so it gets cooled easily. Okay, so from here, we have heard things like many of us, all of us, we have gotten products from the commercial sites, and it's nothing new. But if you look at your handphones, in fact, most of them are products that, like for example, Apple, they got tons of products from everywhere that is already available, and they put it into a product. So I think what's important for our case is that it's good to be resourceful, I feel. To be able to place products that we have in the market and then put it into a single product and make sure that it works. Yeah. So from here, I've come to the end of my presentation. I will allow Xiaoming to carry on with the modification that we have made for the source code. Thank you.
Thank you, Morgan. Okay. Good morning, everyone. My name is Xiaoming, and I will be going through 3 of the source code modifications that our team has done with APM. So firstly, the throttle control algorithm. Now, we are aware that we have a 40 minutes time limit. The aircraft has to come back within 40 minutes. And prior to entering this competition, we do not really know how far we have to fly. So actually, we would like the aircraft to come back as fast as possible. We would like the aircraft to fly at our stipulated ground speed as far as possible. So for us, without airspeed sensor, the default code in the APM flies at a speed that is controlled by its throttle settings. And the control of the throttle settings is such that the output throttle is cruise throttle plus a few other variables that are defined by its current altitude and its required pitch. So there is no variable component inside that allows the default code to allow the plane to fly at any given speed that you want. So bearing that in mind, we have decided to change the source code a little bit so it can fly at our stipulated speed. So the algorithm that we have done up is a very simple sense and adjust logic. You can say that it is a somewhat simplified or modified version of a pure eye controller. Why is that so? I'll explain later. So what it does is that it will extract the GPS ground speed of the aircraft at 50 Hertz. And it will compare with our pre-programmed target ground speed, which in our case is 15 meters per second. We've done some calculations and we feel that 15 meters per second is a very safe speed. So what happens is, if the ground speed of the aircraft is lower than our target ground speed, we will increase the throttle by 2% every 2 seconds. So it gets stepped up every 2 seconds. Now, why 2 seconds? Because we feel that even when the throttle is increased, the aircraft does not respond to change in speed immediately. So we gave a buffer time of actually 1 to 2 seconds in order to allow the aircraft to respond physically. Now, if we do not do that, we have found out that there might be a possibility of hysteresis and oscillations might occur. Speeds up and slow down, speeds up and slow down. Yeah. So this is what we've done. So the end response is, like what I said, the throttle will be increased or decreased at 2% at every 2 second interval until our condition is met. And of course, yesterday the judges have also expressed their concern whether over-throttling might occur. Flies at full throttle all the time. We have also considered that. That's why we have constrained the maximum adjustable component of the throttle to our fixed level. For us, it's -2 to +14. Yeah. But we are also aware that an increase in throttle or decrease in throttle might also result in a change in pitch. But that is not to worry because APM is already stabilized by its pitch navigational PIDs. So the effect is very, very minimal. Okay, moving on to the automatic camera triggering. Now, the automatic camera triggering code builds upon the loiter radius reduction codes, which will be elaborated by Adrian later on. This part of the code sits inside his control loops. So now it's interesting to note that when the aircraft goes into loiter mode, it will speak out a command that is given by math command loiter turns. So using that, we have identified when the aircraft is actually loitering. Now, bearing that in mind, whenever we identify that this command is being given out, we would send a PWM signal to the camera, which will trigger on the camera. How the PWM triggering works is somewhat like this. The camera has an input port which reads PWM signals, and its accompanying software allows you to modify the PWM threshold. Above the threshold, anything above the threshold, the camera will trigger on. Anything below, it will trigger off. So it's a very simple logic. So using the auxiliary PWM output from APN, we trigger on and off when it's in loitering or not in loitering mode. Yeah, and it stays on when it is in loiter sequence. Turns off when it leaves. Of course, the most important part is our camera stabilization code. Okay, as mentioned earlier, our camera has to point parallelly to the ground all the time in order to capture nice pictures. Now, correction in roll is the most important part here because the aircraft has to bank. Pitch is minimal during cruise or loiter, so we aren't very concerned with variation in pitch. So what we do is APM already calculates from its 3 accelerometers. It's already filtered. We can read out the instantaneous roll and bank angle of the aircraft at any given time. So what we do is we extract the bank angle at also 50 Hz. And from that bank angle, we compensate that bank angle negatively, and we throw out the command to the servo that is actuating the camera frame. So that is sorry. Yeah, so this is what we do to counter rotate the mount in order to achieve a stabilized effect. So following which, I'll pass on to Adrian to elaborate more on other source code modifications that we have done to APM.
Good morning everyone, I'm Adrian, and I shall go through some of the other source code modifications that we have done. Now, first and foremost, we'll look at loiter radius increment. Basically, looking back at the mission objective that we are required to fulfill again, there are 2 such zones that we have to cover. So this loiter radius increment actually gives us a very good algorithm for us to cover the search zone with minimal areas of blind spot, means areas that are not covered. So what happens is the autopilot module will actually identify a sequence of loiter turns command, which is mentioned by Semi earlier on. So once it identifies, it will execute the loiter first at the biggest radius, and with subsequent loiter turns, it will actually decrease the radius to the center. Then after which, it will sense for the last loiter command. Then once it sends a command that is once it sends the command that is not loitering anymore, it actually resets the radius back to its biggest radius to allow us to conduct the search again for the next zone. So this is a diagram. Next, I'll go on to the fail-safe feature that we have. Basically, for battery low, what the plane will do is actually will cut its throttle and set the plane to circle with a constant bank angle. Now, the idea here is to actually let the plane descend in a controlled fashion rather than sort of a dropping debris that may actually damage the plane and cause danger to whoever is on the ground. The last fail-safe feature that we have is telemetry. Basically, this sets of code will actually check the input signal to see if there is any feedback for 20 seconds. Once the feedback is lost for 20 seconds, a command will be issued for the aircraft to fly back to its original point of launch to prevent, so that we can do the necessary correction to the aircraft to check to see if there is any issues with the aircraft and allow the aircraft to continue its mission. Now, to conclude, basically taking part in this competition allows us to take what we have learned from the classroom and put it in practical use. And of course, out of the engineering aspect, we also learn time management, and what our team would like to do next time is to actually implement such algorithms in our future UAV projects so that we can actually reduce the search time required. Yeah, that's all. Thank you.